Okay, here we are today starting section 16.1. It's our last chapter, and this is video 23. And so we're going to look back at, so let's recall that when we were in Calc 2, we integrated over straight line intervals AB on the x-axis. So something like this was a classic picture from a Calc 2 course, right? And if you took the definite integral from x equals a to b of f of x dx, and in this case f is positive throughout, this would give you area. And this is sort of the gateway drug into how to integrate, what integration means, but at its core it's really just area. Okay, we're going to extend this to Calc 3. And instead of always, because we're in 3 space now, our curves don't always look like a straight line. They can be, well, curved. And so suppose we want to integrate some function f of x, y, z over a curve, and the curve in this course is given by parametrization. And this is what the notation is here. We use g, h, and k for the coordinate functions, and then we set our our parametric interval at a to b. All right, so then function values are given as what? F of g. I got my g of t, h of t, k of t. I got an extra. There we go. These are the function values at each point along the curve. Okay. So this is really, really similar. Let's draw a picture to get a better sense of what I'm trying to explain here. So here's just some random curve out in 3 space. This is our curve C. This bottom point here will be R of A. The top point here will be R of B. And then the R itself is this position vector emanating from the origin, right? Okay, same idea though. Up here what we did is we called this a little delta x. Well, no, that's not right. I didn't say that correctly. This guy we split up into strips. And each strip has width delta x and height f of xk for some point along. So if this was, it would be some point along there, and this gives us a little area strip, a sub k, and then we add all those up and that gives us the integral, right? We're going to do the exact same thing, but only now we're going to work with a curve, and instead of having a little delta xk, we're going to have a little delta sk, where s is the arc length parameter. We defined this at the beginning of term, and I carried on about it for a while because it turns out to be really important. Okay, but we do the exact same thing. There's going to be n of these little arcs, right, along here. N of these little arcs, and inside each one we'll pick a function value, f of x, k, y, k, z, k, and we just integrate. So we get f of x, k, y, k, z, k, and then the width is going to be delta s, k. And we have k, we have n of these, so k goes from 1 down to n. And this turns out to be our nth partial sum. And then if you take the limit as n goes to infinity of Sn, you get what? You get the interval over c of the function with respect to s, right? So this is a finite differential, and this is a continuous differential. This is a discrete point, and this is a continuous function. Okay, and so definition. This is called the line integral of f over the curve C. Alright, now remember, we use this S, or try to remember, we use this S to make these computations easier, and sure enough, this construction is due to the fact that S sub k is so well defined. But the definition of S sub t is the integral. It's the integral from tau goes from a to t v sub tau d tau, where the v function is the derivative of the curve, right? So to remember, v sub t is dr dt, okay? And so if you look at these two together and you use the FTC part 2, what you get is that ds dt is the norm of v. Okay. So plugging this into, where is that thing? This guy. Right? What you get is, you get t goes from a to b. I got f of g h k. I got the norm of v sub t dt. And this is the working definition of a line integral. Right? So we use the S to well define the theory, and then we translate back to T in order to integrate. Okay. So it's been a while since we've done some parametrizing curves. And so one of the hardest parts of this, because for each one of these problems, part 1 is to find a parametrization for C. And we'll fix this as we go along. Okay, remember if if f is equal to 1, you just have the length of C, and that's all you're finding is the arc length. Okay, let's do an example here. Let f of x, y, z equal x minus 3y squared plus z. And we want to integrate over the line segment C joining the origin to the point 1, 1, 1. Okay. Alright, so here's a parametrization of this curve. Well, it's a line, a straight line curve. That's what I like to call it. It's Ti plus Tj plus Tk, and T runs from 0 to 1. So let's check that. So when t equals 0, I get zeros across the board, so I'm here. And t equals 1, I get I plus j plus k, which is up here. So there's my little line segment C. Okay, we also need V, which is I plus j plus k. We also need the norm of V, which is the square root of 1 squared plus 1 squared plus 1 squared, which is root 3. And now I think we're ready to set up our integral. So the integral of f ds is the integral of, so t goes from 0 to 1, f of g, h, and k times the norm of v dt. So now we evaluate f at triple t, and what do we get? Where's f? Two t minus 3t squared. Root 3 dt. Which becomes t squared minus t cubed, which is 0. Alright, now, what's different about this, well, unique, is that there are more than one way to get from 0, 0, 0 to 1, 1, 1. Right? So we're going to call this example 1 continued. And let's draw another picture here. So this is the point 1, 1, 1. In this example, we parameterize the curve C, and when we integrate it over C, we got 0. what if instead I took the route, I went from here to the point 1, 1, 0, and then went straight up here. Call it this C1 and this C2. And so now we go, alright, C is going to be the union of these two, so I take a different path. Okay, and if we parameterize C1, we get Ti plus Tj, and if I parameterize C2, I get I plus J plus Tk, and all of these have a parametric interval of 0 to 1. So I can take a different route to get there. And I'll get a different answer for my integral. I'm not sure I want to go that far with it, but we'll see. All right. I'm sitting here changing my mind about what I want to do. That happens sometimes when I teach. Let's talk about parameterizations, because this turns out to be a sticking point. Okay. So remember that lines have this form. Here we go. X naught plus V1t, Y naught plus V2t, Z naught plus V3t, where V is a vector parallel to the direction. Right. And so to find this parameterization, right, we start at 0, 0, 0, and the vector is I plus J plus K. So we get T, T, T. And so our parameterization turns out to be 0 plus Ti plus 0 plus Tj plus 0 plus Tk. Oops. And T runs from 0 to 1, which is what I gave you before. So that's not really enlightening, but it gives us a start. Let's find now something a little more challenging. Oops. The line segment from 1, 1, 0 to 1, 1, 1. Okay. Okay, so the vector v that we're wanting is what? It's just k, right? Because this is C2 above here. So this is what we're parameterizing. Okay. So in this definition here, the V is K. Okay. And so here's the parameterization. It's the 1, 1, 0 plus 0t plus 0t plus t. And so when you put that into the parameterization, you have I plus j plus tk. And t goes from 0 to 1. So now the question is, well, here's a fact. If you C is driving me crazy. If you have a line integral f over a curve C, and C is made up of the unions of C1, C2 down to Cn, then this thing they're additive. That's if C is defined this way. Okay. And I'm going to give you some guided practice here. Because I didn't do it in my notes, and I wish I had, and I'm not going to sit here and do it for you. So here's what I want you to do. The integral we just did for an example, it turned out to be 0. I would like you to integrate the same function f, only now you're going to use the other parameterization. And the question is the original equal to, is this equality true? Okay, so just so I'm clear, you're going to parameterize C1 and C2. Do these two integrals and see if they add up to 0. And then I'll catch you in class. And I think I gave them to you. There's the parameterization for C1 and C2. You might do it yourself just to make sure you know what the hell happened there, using this construction like this. And I'll see you in a minute.